Hi students, welcome back. Today I want to talk about chapter 70.3a, the Chatelier's principle, and we're going to look at the change of volume. So hopefully you turned in the worksheet on concentration, change in concentration, and the one on the ice table. So we continue with the Le Chatelier's principle, and now we're going to look at the change in equilibrium due to a change of volume. So let's repeat a little bit about equilibrium expression. Products over reactants, concentration, so between the brackets, and the reaction coefficients become powers. In my reaction equilibrium expression, we only include gases or particles that are in solution. And remember, when we have a value for K, that we call it equilibrium constant, and the value only depends on the temperature. So it's not going to change, only if temperature change. So we're looking for shifts in equilibrium. Last class we looked at removing or adding compounds. Today we're going to look at increasing or decreasing volume, and next class we're going to look what is the impact of temperature. So Le Chatelier's principle, when you do have a pressure on one side, the system wants to go to the opposite side. That's more or less what Le Chatelier's principle is. So what we had for adding and removing compounds, when we're adding the reactants, equilibrium shifts to products. And also when we add products, Le Chatelier says goes to the other side, so equilibrium shifts to reactants. When I'm removing products, so my reverse reaction is less possible, my equilibrium shifts to products. And the same applies for removing reactants. Then my equilibrium shifts to reactants. Removing reactants, so I have more of my forward reaction to products. Now we're going to look what is the impact of increasing or decreasing the volume. Always K value is constant. I do that with two examples. Here I have my favorite reaction, N2 plus 3H2 in equilibrium with 2Na3. Here you see the equilibrium expression, the concentration of Na3 to the power of 2 divided by the concentration of N2 times the concentration of H2 to the power of 3. What will happen when the concentration? What will happen with the concentration if I decrease the volume? So assume we have in equilibrium a concentration of 1m for N2 and H2 and 2m for Na3. When I plug these numbers in my K expression, we have a value of 4. Now we're going to look what's going to happen when I decrease my volume by a factor of 2. Okay, by a factor of 2. Here we have the first situation, K is 4. When I decrease my volume, I increase my concentration because concentration is moles per liter. If I decrease by a factor of 2, my molarity will increase by a factor of 2. So when I decrease my volume by 2, my concentration of N2 and H2 go up by a factor of 2. So they will both be 2m. And my concentration of Na3 also go up by a factor of 2, so it will be 4m. If I plug in these numbers into K, I will see now I have a value for 1. But I said K is constant, so K is 4. And now it's suddenly 1, but it has to be 4. So it has to get back to 4. How do I get that? There are two ways doing that. Or my concentration of products must increase, because K is products over reactants. If I want to increase K from 1 to 4 again, I can increase my products or decrease my reactants. And now you can see I have to increase my products. These are on this side. I have 2 particles, 2 Na3. For reactants, I have 4 particles. So we can say when we decrease the volume, my reaction swifts to the side with the smallest number of particles. So decrease volume, shift to the side with the smallest number of particles. And probably you will not be surprised when we increase the volume, it's all the way around. Here we have the situation we started with. Now I'm going to increase my volume by a factor of 2. Now the concentration decreased because I have a larger volume, my concentration is going to be lower. So now my new concentration are 0.5 m for N2 and H2, and instead of 2m, I have now 1m for Na3. When I plug in these numbers, I get a value for K is 16. But K must be 4 because it's only changing when the temperature changes. So how I come back from 16 to 4? Or I decrease my products because it's products over reactant, or I increase my reactants. So increase my reactants is on this side, and that has the largest number of particles because I have 1, 2, 3, 4 particles, and on this side I have 2 particles. So increasing the volume, my equilibrium shifts to the side with the largest number of particles. So let's summarize it. A decrease of volume, that means an increase of concentration, but decreased volume, equilibrium goes to the side with the smallest number of particles. If I increase my volume, that means a decrease in concentration, then my equilibrium shifts to the side with the largest number of particles. So decrease volume, smallest number of particles. Increase volume, largest number of particles. So you see, decrease, smallest, increased, largest. The book is telling you a little bit that talks about pressure. When I decrease the volume, there are more particles on a smaller area. There's an increase of pressure. And then the system will offset that. This goes to the other side, to the side with the smallest number of particles. It's the same explanation what I just showed you, but a different way. If you're interested, just read in the book about it. Okay, let's have a summary so far about shifts in equilibrium. Adding reactants shifts to products. Adding products shifts to reactants. Removing products shifts to products. Removing reactants shifts to reactants. Decrease volume shifts to the side with the smallest number of particles. Increase volume shifts to the side with the largest number of particles. Next class we're going to look what's the impact on temperature. And then we had all the different possibilities for shifts in equilibrium. So for next class, I want you to study chapter 70.3a, especially on volume. And there's an online worksheet, Le Chatelier principle, or change in volume, and also concentration. And that's due on Monday. Okay, guys, that's it for today. Good luck. Bye-bye.